So we'd last left off talking about the transition elements, which are also metals and are found in the center of the periodic table. They contain two rows that lie below them called the intertransition elements. Their names, lanthanide and actinide series, as you know, come from the fact they start with the element lanthanum and actinum. I don't know that this next statement is entirely true. I'm not sure that their natural abundance is still only 0.1%. I think the reason why they were called the rare earth elements is because they were so hard to separate from each other, not necessarily that they occur in minor amounts. And that's one of the big pushes these days, is to find a natural source of our rare earth elements, because we use them in so much of the electronics that we use today. And currently there's a worldwide dependence upon rare earth that is supplied by the country of China, which tightly controls the pricing and the supply. All of the actinides are radioactive, and any one that is beyond uranium do not occur naturally in nature. They're created by human beings making new synthetic elements in things like cyclotrons or linear accelerators, or as a byproduct of nuclear explosions. Now, if you get a chance, please go to our site to look at the video about Dr. Glenn Seaborg, a very famous chemistry professor at UC Berkeley. He passed away several years ago, probably about 10. Nicest, most gentle guy you could think of, but as a young man was one of the group that worked on the Manhattan Project, finding how to create the nuclear weapon before the opposition in World War II did, the Axis. You will see in this video that he talks about how, as a young man, he was suggesting radically different organization of the periodic table, and people were warning him, "Don't do it, Glenn, you'll ruin your career." And he is fond of saying, or was fond of saying, he had no career to ruin, so he took a big chance, reorganized the periodic table so it looks like what you and I see today, and in the process won a Nobel Prize. Do cool things in science, you get cool stuff named after you, and so one of the new synthetic elements is named seaborgium. So please take a moment and go to Moodle and check that out if you can. On the far right side of the periodic table are the nonmetals that we've studied before. They're not necessarily generally gases, so don't think that nonmetal equals gas. Nonmetal could be solid, liquid, or gas. They are not good conductors of heat and electricity. Bromine is the only liquid nonmetal. If they're solid, they're brittle, not malleable. And they have a group within them, Roman numeral 7a, called the halogens, and that means salt formers. The reason why this group is highly reactive is because it has 7 valence electrons, each of them do, and they're always on the prowl to steal one electron, typically from a metal on the far left side of the chart, and consequently make very reactive sort of reactions. So chlorine, for example, will be on the prowl to steal an electron from, say, sodium to make sodium chloride. Of course, the reason why they're stealing electrons is to fool themselves into thinking they are isoelectronic, the same electron configuration as the stable group of noble gases immediately to the right of them. And as you know, most of our atmosphere is made up of nitrogen, probably 79%, and about 20% is oxygen. Both of those are fairly numerous elements in the Earth's elemental lineup, so to speak. Carbon is a very important nonmetal. It's found in more compounds than all other elements combined, and that's because it forms the basis of life. Essentially, the bonding sites that carbon can achieve can allow it to create long chains or cyclical molecules, rings, which make up all the biochemical molecules which make up life as we know it. I don't know if this sentence would be entirely true, that the melting points of the nonmetals tend to be lower than those of metals. For example, carbon in the form of diamond has an incredibly high melting point. And here's a picture of 2 forms of carbon. Carbon in your pencil, which we call as a misnomer lead, it's really carbon in the form of graphite. There is also carbon in precious diamonds, and the difference between those two is a result of how the atoms are bonded to each other, which we will study in some detail. So to sum up our properties of metals and nonmetals, I think we know metals are shiny, nonmetals are not. Metals are malleable and ductile. Solid nonmetals are often brittle. Metals, of course, are conductors of heat and electricity. Nonmetals do not. Metals play pretty fast and loose with their valence electrons, losing them quite easily. Nonmetals hang on to their own valence electrons and, in fact, are stealers of electrons, as we will also learn. Now, bridging the gap between metals and nonmetals are the metalloids, or as we refer to it in Europe, semimetals. And they have physical and chemical properties that are sort of intermediate between metals and nonmetals. Silicon and germanium are really important metalloids because they're critical for computers and electronic circuitry. We call them semiconductors because they have the ability to sort of conduct electricity. There's a solid chunk of silicon that they're slicing off in thin wafers, and you can etch onto the surface of that wafer a microcircuit to fit into an electronic device. So as you mentioned, a semiconductor is an element that doesn't conduct electricity as well as a metal, but does so better than a nonmetal. And you can add certain dopants to semiconductors to increase their ability to conduct electricity. Of course, silicon made the computer revolution possible. Our television sets, our computers, handheld electronic games, cell phones, all of them depend upon the semiconductor capability of these metalloids. And that last black slide was a reminder to me to tell you also, posted on our site is going to be a video about semiconductors as well, so take a moment to view that. When you go to Moodle, you will see under the Chapter 6 heading a number of short videos to watch. Now, I'm going to slow down here a little bit because we are now going to learn the first of our atomic or periodic trends, and the one we're going to learn today is atomic size or radius. And we've already used this as we've started our periodic law cut and paste, build your own periodic table activity. But now I'd like to slow down and define a few things and explain a few things about the trends. How closely an atom lies to its neighboring atom determines its size. And if you look at half the distance between two adjacent atoms that are bonded, that's the distance between their nuclei. The definition is to take half of that distance and call that the size or radius of your element. So this would be a nonmetal here, and this is a diatomic molecule. Remember, those are the ones that come in partners of two. And let's take a little refresher here and remember our diatomic elements are those Brinkelhoff guys. Do you remember those? They're all the ones that have a partner. Bromine, that's the Br, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. I suppose acetine is also diatomic, but being radioactive, you and I don't deal with that very much, hopefully. So these are our diatomic elements, and the definition is pretend you have two elements that are bonded together, the same kind of atom. Take half the distance between them, and that will tell you the true definition of what is the atomic radius. I like to say the Brinkelhoffs, not necessarily Mr. Brinkelhoff. That's a confusing mnemonic if you ask me. Okay, now if you look at this chart, I think the trend should be pretty obvious. I like to take it from top to bottom and indicate that going down any group, atoms get bigger. Going from left to right, and of course there's always going to be some inconsistencies in the periodic table, but in general, going from left to right, atoms get smaller. Now, I'll be able to explain this to you using a couple of terms that you're going to need to use when you explain it to me. The arrows that you see here are pointing to the larger size. So this arrow is pointing as you go down, it gets larger. And this one says as you go from right to left, they get larger. I like to say left to right, they get smaller. You pick it. Size will increase going across from right to left, or you could say it decreases from left to right. Now, there's some subtleties to this, which I will go over again in class, but let's take the easy one first. As you go down a column, it's pretty obvious that each time you jump down a row, you're adding a whole nother energy level worth of electrons. So that makes it easy to understand why the atom gets bigger. But what you probably don't know about or aren't able to figure out is this thing called shielding effect. And that's when lots of inner electrons shield the outer electrons from the pull of the positive nucleus. Essentially, they act like a buffer. So if you're the electron that's on the outermost energy level, you don't feel that pull of the nucleus as tightly. So going down, atoms get bigger primarily for two reasons: adding an entirely new energy level to the outer edge every time you bump down one row, and secondly, the shielding effect is increasing. So here's that definition of shielding effect again. It's when lots of inner electrons shield or protect the outer electrons from the pull of the positive nucleus. So what happens to that shielding effect as you go down? It increases. Now what happens to your shielding effect when you go across? This is interesting in that it stays the same. So what I'd like to do is to back up to that previous slide and take a look at that for a second. You would think at first, going from left to right, every time you bump over one box, you're adding another electron, and you would think, oh, I'm adding another electron to the outermost energy level, my atom should be getting bigger. What you're forgetting is that each time you bounce over from one box to the next, you're not just adding one electron, you're also adding a positive proton in the nucleus. This is called increasing nuclear charge. And if it's a greater positive pull in the nucleus, it's like a siren call to the outermost electrons. It pulls them in tighter and closer to them, just like you have a dog on one of those retractable leashes. So going from left to right, the reason why atoms get smaller is, one, the shielding effect doesn't change. I'm not adding a whole nother layer of electrons. I'm adding electrons to the outermost layer. And secondly, the nuclear charge increases. A positive pull of the nucleus for the outermost electrons reins them in. Now we'll discuss that again. I think I will be able to embed or actually add onto Moodle a QuickTime video that shows the impact of the shielding effect. That's a good stopping point, and we will pick up the next time talking about ionic radius trends.